Okay, so continuing chapter 2 here, section 2.2 is subsets and Venn diagrams. Okay, we're going to start off talking about Venn diagrams, which is basically just a visual representation of the relationship between multiple sets. You've probably seen a Venn diagram before. Usually the sets are represented by circles, and maybe there might be some overlap between the sets. There doesn't have to be, but this is kind of the most classic case of a Venn diagram. Two sets with a little bit of overlap and a lot of stuff that is not overlapping between the two sets. Okay. And we're also going to be talking about the concept of a subset, and that's going to tie really nicely into our Venn diagram pictures. Now, last time I gave you a list of kind of terms to know at the top of the lecture. I'm not going to do that here because this lecture is more about pictures, a couple definitions with subsets, and then a way to count a number of subsets at the end, but not nearly as many terms to know in this section. So let's get straight into Venn diagrams. So like I said, you've probably seen a Venn diagram like this. Two sets represented as circles with stuff in the circles. You may give them a title. We usually use capital letters for our sets, just like last section. So I would name this set A and this set B. And according to this picture, there are things in A that are also in B. In other words, there's overlap between them. Now, we're also going to put rectangles around our Venn diagrams. This is going to represent the universal set that both of these sets live inside of. So that's the same universal set as the last section. The universal set will depend on the context of the problem. It could be the English alphabet, it could be the natural numbers, it could be all of the people in a university, it could be anything. It just depends on the context of the problem. But the universal set is where the smaller sets live. And we're not just going to see pictures like this. We're going to see distinct sets where there's no overlap. Maybe there's no overlap here, right? And we're going to see sets maybe where there's complete overlap, and that's where we're going to get into the discussion about subsets. So maybe set A is here and set B is completely encased in A, or vice versa. It could be the other way around. So we're going to talk about this situation later. In this situation, B would be called a subset of A, but we'll talk more about that later. We're also going to be looking at Venn diagrams that have three sets in them, or more possibly. We probably won't go above three too much. But we're going to be looking at how three sets can overlap with each other. It gets a little bit more complicated. But actually, let's see, we're going to look at that in section 2.3 and 2.4. So we're just covering the basics today. So I'm going to start with example 1 from the lecture notes. So from those lecture notes, let me get over there. Example 1. From notes. I'm going to look at getting a better light source that's not behind me. That's my ceiling light that's casting these dark shadows right here. I'm going to look at getting a lamp, maybe to offset those shadows a bit. Okay, example 1 from the notes says to use the diagram to answer the following questions. Okay, so I've got a statement in parentheses there at the top for myself. So here's how it's going to work. I'm going to have a Venn diagram. So this is basically the reason I wrote it like that is it's really hard to, in the way that I type up my lecture notes, it's really hard to get pictures in there. So I just told myself to draw this on the board. Of course, this isn't a board. Alright, so we've got T is equal to TJMD. Let's see, do any of these overlap? No. So this is actually also example 1 from the text. So I've got, let me draw it the same way they do, oriented the same way. T, S, and V. U here is the English alphabet. C, P, this is, and S is K, A, S. So these are all letters in the English alphabet. U is the universal set. It is the entire English alphabet, and each of these are distinct, meaning they don't share any letters here. They don't share any letters. Part A says to list the elements of the sets STV in roster form. So we're pretending like we don't know what they look like in roster form. So let's say list in roster form. Using shorthand because the full statement is written out in those notes. S is the set K, A, S, just like that. The set S is the elements K, A, and S, all separated by commas. T is the set T, J, M, D. And V is the set. So this is just a kind of a little review of last section, right? Roster notation, or roster form, or roster method, whatever you want to call it. The point is it's roster, right? It means like a roster, like you're listing things out. Okay. B says to find the cardinal number of S, the cardinal number of T, and the cardinal number of V. So that's a capital S there. The cardinal number, but remember all that means is the number of elements in each set. So the cardinal number of S is equal to 3. The cardinal number of T is equal to 4, because there are 4 letters. 3 letters in S, 4 letters in T. And the cardinal number of V is also 3, just like S. Okay. Now the next one's a bit more interesting. They say, find the complement of T. Find the complement of T, and we'll list our answer in roster notation. Alright. So in set builder notation, this is just kind of the definition of a complement, like I wrote last section. It's the set of all elements. Now I better not use a T here, like a little t, because a little t is actually an element of the set. So I'm gonna use like an X, which even it's a little bit weird using any letter here because the elements of these sets are already letters, but X is okay. X such that X is in U, so X is an English alphabet letter, because that's what U is here. That's what the universal set is. And X is not in T. That's the definition of a complement. It's the stuff that's in the rectangle. If we look at this picture, it's the stuff that's in the whole rectangle, including S and V, this entire rectangle, except we exclude this bubble here. We exclude the set T. Now, this isn't the solution to that. This is just a definition of a complement. For any complement, I could put, any set, this is the definition of a complement, the stuff that's in the universal set and not in the original set. But when it says find the complement of T, that means actually list it in roster notation. So what are the letters that are in the universal set and not in T? Basically, I'm going to list out the entire alphabet, but I'm going to exclude TJMD. Okay, so I'm going to say A, B, C, Now I don't want D because D is in T. So these are the ones I'm excluding. D, okay, so no D, and then E, F, G, H, whoops, I, no J, okay, J, K, L, no M, N, O, P, Q, R, S, U, V, so I excluded T as well, and then W, X, Y, Z, oh, just enough room. It's a long set. There are 22 elements in this set, right? How do I know there are 22 elements? Well, because U is 26 elements, because there are 26 letters in the English alphabet, and T is 4 elements, so the complement of T should be 22 elements. And there they are. So this is the entire alphabet except for these 4 letters. I want to draw a picture of what that is. Okay. Let me redraw. Well, do I? Yeah, that's fine. I'll redraw it. No, I can draw over this one. I'll draw over this one. I'll just use a different color. Okay. T complement. I'm going to draw T complement here. Or I'm going to shade in the stuff that is T complement. So remember, the complement of a set is everything in this rectangle except for the stuff that's originally in T. So if I was going to like shade in what T complement is, it would be all of this. Including KAS, right? Including that set. Ooh, these are nice lines. Including the V set. I'm going to try and make sure. Okay, the lines are not as nice now. That's okay. The point is, I'm excluding T. I'm shading in what is inside of this set, the T complement set. So this is being excluded here. That's T complement. So it does include S and V. Okay, last part of this question or example is S equal to V. Is S equal to V? Well, remember, for S to be equal to V, they should have exactly the same units. They don't, right? S is KAS, V is ECP, so the answer is no. They have different elements. Now, is S equivalent to V? Remember, equal and equivalent are two different things. Yes, they are. Why? They have the same number of elements. They have the same number of elements. I could also say they have the same cardinal number. It's kind of a fancier way of saying they have the same number of elements. They have the same cardinal number. Remember back here, these are their cardinal numbers, and S and V have the same cardinal number, so they are equivalent. That's just a fancy way of saying they have the same number of elements. Okay, good. Now. Okay, this next example is from the text. Example 2 from text. Yeah, I'll use blue for this. Example 2. Now this is from the text, not from the lecture notes. I skipped this one in my in-person lecture last semester because I just didn't really think it was necessary. And I changed example 2. You'll see in my lecture notes, example 2 deals with number sets. We're going to do that one as well, but this is the one from the text on page 52. and it says that there is an increasing number of electric vehicles on the roads in the United States. The number of charging stations available for these cars varies from state to state, and the states with the most charging stations are California, Florida, Oregon, Texas, and Washington. And they give us a picture. They give us some numbers and some pictures, or a picture. Let's make it a bit bigger. They say U is all public and private electric charging stations in the U.S. And they're saying this inside. The cardinal number of U is equal to, what is that, 19,996. Then we've got those 5 states. So let's see, I need to make sure there's 1, 2, 3, yeah, so about this big. See, that's going to be California, Oregon, Washington, Florida, and Texas. So, C for California, and they tell us that the cardinal number of C is 5,415. 5,415. For Oregon, O for Oregon, there are 923. 923. Washington, there are 1,339. 1,339. Florida, there's Washington. Florida, there are 1,009. So, what's going on here is, instead of listing every single element inside these sets, like we did with the letters, we're just listing how many elements are in each of these bubbles, each of these sets. By the way, that's the cardinal number of O there. It looks like 101, but it's not. It's line, O, line, for cardinal number of the set O for Oregon, 923. Okay, so why is this useful? Well, first of all, because there's just a ton of these things. It would be impossible to draw a picture of this, right, and like list all of them. Plus, why would you need to list all of them? They don't have distinct names necessarily. Or maybe they do, but that's not the point of this data, right? It's all just about the number of things. That's why each of these, inside each of these sets, you just have the number of items. Now, it would not be correct for me to write a C. Like, for instance, I could, why not just do this, like say C, and then just do this inside? Why is this not correct? Because this would mean that the set C has the element 5,415. That this is the only element of that set. So this means that C is equal to that set with just a single number in it. A big number, but just one number. But that's not what this is, right? C is supposed to be a set of charging stations, right? So this is telling us the number of items in the set. This is not the correct notation for that. So it's important to list it this way, or to write it this way. Cardinal number of the set equals, and then the number. So that we know we're talking about the number of things in the set, and not just saying what's actually in the set, not the items that are in the set. Okay, then they ask us some questions that are pretty straightforward once you have this picture. Part A says, which state has the most electric charging stations? Of course, it looks like that's California, pretty by a long shot. Which state has the second highest? Looks like Texas. So once you have this, it's pretty easy to answer these questions. How many do the top 5 states have altogether? So you would just find the sum. You would just find the sum of all these numbers, and it looks like 10,299. How many charging stations are in the U.S., but not in one of these 5 states? So that's a good question. How many exist outside of these bubbles? In other words, in all of the other 45 states, Arizona, New Mexico, Alabama, Georgia. What about all these other states? Well, we would take the total of these 5, take it away from the total in the U.S., because that's what the universal set is, right? The total number, the universal set is all of the charging stations in the U.S., so this 19,996 is how many are total in the U.S., including these 5. So we add up those 5 to get this, then we'll subtract that from 19,996 to get the number of charging stations that are not in one of these 5 states. So, 9697. So these 5 states definitely have the majority, right? I mean, just in these 5 states, they've got more than half of all charging stations in the U.S. Well, at least as of the time this book was published, right? So, I'm sure there's a lot more now. Okay. Let's look at example 2 from my notes. It says, so this is from the notes. Example 2 from notes says, let U equal the set of natural numbers So my universal set is the set of natural numbers. Remember, that's 1, 2, 3, 4, etc. Not 0. Let A be the set of all elements x such that x is in U, so it's a natural number, and x is even. Okay, so that's like 2, 4, 6, 8, 10, etc. And x is less than 10. Okay. So that severely limits this set. That's okay. Let B equal the set of all... I didn't write it correctly in the notes. I missed the initial part of it. The set of all x such that x is in U, and x is odd, and x is less than 10. Draw a Venn diagram to describe the relationships between these 3 sets, U, A, and B. And then they ask, what is the cardinal number, or list A in roster notation, list B in roster notation, what is the cardinal number of A, what is the cardinal number of B. I'm going to say that the easiest part of this is going to be to list these in roster notation first, probably, because they're such small sets that we can pretty easily list them in roster notation. So A is equal to, so I'm going to be a little bit informal about how I'm solving this example. I'm not going to write, parts A, B, C, D, E. We're just going to do it all. We're not going to do it in that order, but we're going to solve all those problems. So A is equal to the set of all natural numbers, which is an infinite set, so maybe roster notation's not the best idea, but it's even. Well, that's still infinite, but it's also less than 10. Okay, so I've got numbers like 2, 4, 6, 8, and that's it, because it has to be less than 10, so I'm not including 10. So there it is, there's A, just 4 elements. What about B? Oh, so, by the way, since I said 4 elements, I might as well list that the cardinal number of A is 4. Okay, what about B? Well, I've got the natural numbers start at 1, so 1 is odd, 3 is odd, 5 is odd, 7, 9, but that's it, because in this set, we want to be less than 10 as well. And the cardinal number of B is 5. Now, is there any overlap? So when you draw your picture, you need to ask, is there any overlap The answer is obviously no, because these are all even, these are all odd. Okay, so that's the last thing, that we need to do, is draw this picture. Draw the rectangles for all the natural numbers. We should draw them without overlapping, because there is no overlap between these sets. They don't share any values. So I'll just draw A and B, and that's it. That's all I suppose if I wanted to be, since they're such small sets, I could list all the elements in here. I suppose 2, 4, 6, 8, 3, 5, 7, 9. Gets a little cramped though. But that is it. That is it. Okay. So then I ask a question in the lecture notes that says, why didn't A and B overlap in the picture? Well, because literally there is no overlap in the sets, right? There's no shared values. There are no shared values. So the diagrams do not overlap. Now, I also have a note to myself to say, give another example of things that do overlap. So let's add another set and draw a new picture. Okay, so example 2 continued, but with a new set. Let C equal the set of all x such that x is in U, so still in this universal set. And let's see, what do I want to make it? Tell you what, let's list it in roster notation, just to make this easier on all of us. So C is equal to the set 1, 2, I don't want to make my picture too complicated. 1, 2, 10, 11. Okay, 1, 2, 10, 11. How could we make that work? How could we make that work? Okay. So we're going to need a new picture. So we're going to draw a picture with A, B, and C. And U. The rectangle is the universal set. There we go. Okay, so A is the set 2, 4, 6, 8. It does overlap with C a tiny bit. Here's A, and here's C. Here's A, and here's C. What is in the overlap between A and C? It's a 2. It's a 2, right? So what do I draw over here? What's left in A? Well, just the 4, 6, and 8. Because the 2 is in there, right? So the 2 is in A, and the 2 is in C. So I've not discounted this 2 from being in A. I've literally just taken it from where it was floating by itself, just with everything else, and just scooted it over in the circle so that it's in this overlap with C. And B also overlaps with that element 1 with C. So here's B. Okay, and the element 1 is in B and C at the same time, but what's left in B? Well, the 3, the 5, the 7, and the 9, right? So it's still the same 5 elements in B, 1, 3, 5, 7, 9, except that B is scooted, 1 is scooted over to overlap in C. By the way, there are still 2 numbers that are in C that are not in A or B, 10 and 11. There we go. So we've got some overlap here. Some overlap between these two. But you notice A and B are still not touching because they're still distinct. When I say distinct, that means there's no shared elements between them. There's no overlap. Okay. So that's kind of a bonus example there. Okay. Let's talk about subsets. Okay, so the definition of a subset is you've got to have two sets, first of all, to talk about this definition. B is a subset of A if every element of B is also an element of A. And we write that as B, and then this little symbol, A. It's like a C with a line under it. This means every element of B is contained in A. You can kind of think of it like a less than or equal to symbol. That's not what it is, but in a way you can think about it like that, because if every element of B is contained in A, doesn't that mean that B is like smaller than A, right? So B is less than or equal to A. But that's not how we read it. That's subset. We would say B is a subset of. B is a subset of A. So that symbol is a subset of. B is a subset of A. Okay. Example. Let's do an example. This will be an unofficial example. Let's let A equal the set 1, 2, 3, 4, 5, 6. B equal the set 2, 4, 6. I could write here that B is a subset of A. Why? Because every element in B, the 2, the 4, the 6, they're all in A. What does this mean as a picture? If I drew a Venn diagram of this, and I didn't name a universal set, but let's just say that U is the natural numbers again, just to make it easier. Nothing weird going on here. So if I drew a picture of this situation between A and B, A is there, that's 1 through 6, and then B is inside of it, completely encased inside of A. Completely encased inside of A. So the 2, 4, 6 is all the way in here, 2, 4, 6, and then the 1, 2, 3 is out here. So the important thing to note about this picture is that 2, 4, and 6 are still in, 1, 3, and 5, not 1, 2, 3. Okay, 1, 3, and 5 are out here. 1, 2, 3, 4, 5, 6. Okay, so the important thing to note here is that 2, 4, and 6 are still inside of A. A is still all 6 of these numbers. B is the one with a more limited set. B is just 2, 4, 6. B is just 2, 4, 6. And A is all 6 of them. And we say here that B is a subset of A. B is a subset of A. Okay. Let's see what example I've got here in the notes. Example 3. This is from the notes. It says that let U equal the set of all elements X such that X is a student at JSU. Okay. Okay, and we're going to let W be the set of all students at JSU majoring in spelled computer wrong, majoring in computer science with a minor in business. X is, tell you what, why did I rewrite that? I'm going to say X is in U, first of all, so X is in the universal set. It's a student at JSU, and X is a student majoring in, I'll say CS for computer science with a minor in business. Let's let Y, capital Y, be the set of all X such that, of course, X is a student at JSU, and X is a student majoring, oh, I should capitalize business because it's a minor here. Okay, majoring in computer science. Okay, there we go. Now, what do we want here? Draw a Venn diagram to represent these three sets, and then say which ones are subsets of each other. And then part C is a technical question. Is Y a subset of Y? So can a set be a subset of itself? Well, we'll get to that, but let's talk about the relationship between these three first. Okay. So we've got universal set, that's easy. It's just a rectangle. So these are all students at JSU with different majors. Then we've got W, are the students with a major in computer science and a minor in business. And Y are just the students majoring in CS. Which set is the bigger set? Okay, which set is the bigger set? Y. Because Y has all of the students majoring in CS. They might have minors in business, they might have minors in mathematics, they might have minors in accounting or biology. This is all of the students majoring in CS. W is a more specific set. It's not as general, right? It's just the students majoring in CS and with a minor in business. So Y is the bigger set, and in fact W is completely contained inside of Y, because every student in W is majoring in CS, meaning they live in the set Y. So I can take Y, which is the bigger set, draw it like that, and then the set W inside. So when you've got sets that aren't dealing with numbers or letters, like something that's easy to write down in roster notation, you've got to think a little bit more abstractly, step back from the problem, and just think about it using, I don't want to say common sense, but just, it's not, there's nothing to picture here. Whereas with this set here, this little example here, I could literally list the elements of the set out, and I can literally see, oh look, the 2 is inside A, the 4 is inside A, the 6 is inside A, so clearly this is a subset of this, because I can actually see it happening. But here, it's not as easy to see happening, because I can't write down all of these elements in these sets, because first of all, I don't know all the students at JSU majoring in CS with a minor in business and other minors. Plus, I just don't want to do that, because it's probably hundreds of students. So it's just not reasonable to write them all down. So you've got to think a little bit more abstractly and think about which set is inside of the other set. Which set is more specific? Okay, now let's answer some questions. We did part A. Part B says, is Y a subset of W, or is W a subset of Y? So I'll list it this way. Which is correct? Which is the correct way to say this? I'm going to have to cover this up a little bit. Y is a subset of W, or W is a subset of Y? Well, the smaller set should be on the left. W is inside of Y. W is a subset of Y, so this one is correct. Okay, and part C says, now this is an interesting question, is Y a subset of itself? Well, the definition of subset says every element of, so in this case, every element of Y is contained in Y. Is that true? Yes. Yes, because every element of Y is contained in Y, of course. Now, this is an important fact because what does this mean? Any set can be a subset of itself. It's just kind of a technicality. Any set can be a subset of itself. Okay. Let's actually keep talking about this idea that any set can be a subset of itself for a second, because it's going to lead into the next definition. So say I have one set A is equal to A, B, C, so the first three letters of the alphabet, and B is equal to that same set, A, B, C. So same sets, just different names. What I can say is A is a subset of B and B is a subset of A. Because in fact A is equal to B here, right? So this subset thing works in both directions. So what we want to do now is we want to have a new definition that's a little bit more strict. A new definition that's a little bit more strict that says, hey, you can only be subsets of each other or proper subsets of each other if one is completely contained in the other and not the other way around. Like, we want to be able to say, we want to be able to distinguish between weird situations like this where the sets are just equal to each other and situations like this where they are actually, one is actually completely contained in the other, and it's not a weird technicality where they're equal to each other. Like, this is an actual proper subset of this, and that's the actual definition. It's proper subset. So let's get that written down. So a proper subset, going off the notes here. First of all, you start off with the definition of a subset. Proper subset means a subset, so basically starting off with the definition of a subset, and the sets are not equal. And the sets are not equal. The way I write it in the notes is, when B is a subset of A, and A contains at least one element that is not in B, then B is said to be a proper subset of A, and is written, so it's written, by the way, like this. B is a proper subset. So, remember earlier when I said you can think of the subset definition as being less than or equal to, like B is a subset of A. This little symbol is kind of like less than or equal to. It's smaller or it's the same size, right? Because the or the same size thing occurs right here when the sets are equal. If we drop that or equal to part, the little line under the symbol, then it becomes a proper subset, and now B has to be smaller than A. I cannot have this situation where they are equivalent to to each other, or equal to each other. I should say equal, because we're being careful about the difference between equal and equivalent. So B is a proper subset of A if it is completely contained in A, but it's not the same as A. It's not that weird technical situation. Okay, so let's look at example 4. Or tell you what, before we do that, let's go back and look at all the examples that we've seen and mark the ones that we called subsets that are actually also proper subsets. But one thing before, let me make one more thing clear. Let's say it this way. If B is a subset of A, so the old definition, then B might be a proper subset. It could be. In fact, it's only a proper subset if it's not equal. But if B is a subset of A, if it's a proper subset. If B is a proper subset of A, then definitely B is a subset of A. If B is a proper subset of A, that means completely contained and not equal, well then surely it's also a subset of A. You could think about it like this. If x is less than 3, then isn't it true? So think of some number less than 3. No matter what you think of, it's always going to satisfy this. X is less than or equal to 3, right? If you picked 2, then that's also going to be true here. Now the opposite is not always true. If x is less than or equal to 3, so think of some number less than or equal to 3. What's the closest you can get? Well, at 3, right? Then x is less than 3 only if what? It's true for all numbers. If this is true, then this is true all the time, except for that number right up at the edge, right when they're equal. So this is kind of the analogy I'm trying to make, or the connection I'm trying to make between these less than or equal to and less than symbols relating to proper subset and subset. Okay, I hope that makes sense. It's a little bit of a stretch, but it can help you to remember that this is a more strict symbol, just like this is a more strict symbol, and this is a less strict symbol. So if you can get into this club, then you're definitely in this club. But if you can get into this club, you may or may not be in the... I'm recording, but you may or may not be in this club. Okay, so where are we now? Let's do that example 4. Sorry. We were going to go back and look at all of the examples we did that are subsets and see which of them are also proper subsets. So let's go back to the beginning of our notes from this section. This is just Venn diagram stuff. We weren't talking about subsets there. We weren't talking about subsets there. Now these are overlapping, but there's no, oops, let me get scooted up here. These are not overlapping, so clearly no subset going on here. These are overlapping, but not completely anywhere, so no subsets going on here. Okay, now we start talking about subsets. Now look here. B is completely contained in A. It's a subset, right? But they're also not equal. So we could actually say, we could come back here, now that we know the definition of, I wanted to use a different color. Whatever. I'll use green. Can actually say that B is a proper subset of A in this case. B is a proper subset. Now, what about the next example with these students from JSU? Yes, W is also a proper subset of Y because it's completely contained. And down here, What about these two? They're subsets of each other, but are they proper? No. A is not a proper subset. It is a subset. This is that technicality. When they're equal, they can technically be subsets of each other, but they're not proper subsets. They're not proper subsets. Okay, cool. Now let's do example 4 from the notes. Example 4 says, let capital X equal the set ABCD. Is Y equal to ABC a proper subset of capital X? So, is Y, which is equal to ABC, a proper subset of X? In other words, now that I've identified what Y is, I can say, is Y proper subset? That's supposed to be like a little C symbol. Is Y a proper subset of X? Well, you look at these sets. First of all, is Y a subset? Is it completely contained in X? The answer is yes. And also, is Y not equal to X? And the answer is yes. So, yes. Y is a subset of X, first of all, because it's completely contained in X, and since Y does not match X, that means it is proper. It's only proper if they don't completely match, so that's not equal to there. They don't completely match. Part B says, is Z, which is equal to the set, what is that, BACED, a proper subset of X? So, in other words, is Z, just rewriting the problem here with the symbol, a proper subset of X? Is Z a proper subset of X? Okay. Well, don't they... Wait. Did I mean to put E in there? Oh, look at that. No. To be a proper subset, you need to satisfy two things. You need to be a subset, and you need to not be equal to the bigger set. But Z is not even a subset. So it doesn't even pass the first condition, because it's got an E in there. X doesn't have an E. X doesn't have an E. Wait, let me double check. Yeah, okay. Yeah, X doesn't have an E, so it's not even a subset. So we don't even need to check, obviously, the second condition, because it's not even a subset. So of course it's not going to be a proper subset. Here's a good question. Is the null set, or the empty set, a proper subset of X? Is the empty set a proper subset of X? The answer is yes, technically, because what is contained inside of the empty set? Nothing, right? So technically, the definition of proper subset says that you need to be a subset, meaning everything in this is in this, but that's just inherently true because there's nothing in this, and you need to not be equal to the other set, and clearly it's empty, so it can't be equal to this X set. So the answer is yes, and I'm going to write it in green because this is another fact, like another technicality coming up. So yes, the empty set, I'm going to say the two conditions that make a proper subset, which is that you need to be a subset, and the empty set is not equal to X, so the empty set is a subset, proper subset. Alright. Since the empty set is a subset of X and the empty set is not equal to X, the empty set is a proper subset of X. In fact, the empty set is a proper subset of every set. Is this completely true? Think about that. Can the empty set be a proper subset of every single set? Wouldn't it be a subset of everything because it's smaller than everything? But what about the second condition? There's one set it won't work for, except for itself. I can say one thing though, X is a subset. Remember, subset's a less strict club. This is a stricter club, so is a subset of every set. Oh, I don't know why I wrote every set. Okay, twice. Including itself. Right, because a set can be a subset of itself. We answered that earlier. Can't be a proper subset of itself, though. Okay, now we got one more thing to talk about, which is numbers of subsets and numbers of proper subsets. Okay, so in the notes I say as an example, list all, what do I say, subsets and proper subsets? Well, anyways, I'm going to change it a little bit anyways. Let's do this. List all subsets and proper subsets of, and let's make the set A, B, C, D. I know that I put an E in there in the notes, but that's going to be a little bit excessive. You'll see why in a second. List all subsets and proper subsets of X. Well, all the subsets well, I know the empty set. Let's start with the smallest ones. The empty set is going to be a subset, right? It's a subset of every set. What about the singleton sets? Sets with just one element. That's a subset, right? Sure. But then that means all of these are as well. Right? Each of those are elements of the set, so if I put them in a set by themselves, then surely this is a subset of that, as is this, as is this, as is this. But then what about this set, A, B? Sure, why not? And then if that's the case, then what about C, D? Good, okay. What about AC? Okay, and I want to make sure I don't copy any of these, or write them twice. So AB, I've got CD, and I've got AC. How about AD? Okay, AD. What about, do I have BC? Not yet. Do I have BD? I don't think so. Is that all the two sets? The sets of two? 1, 2, 3, 4. There's 6. Let's see. 4, 2, 6. Is that 6? 12. Yes. Okay. Anyways, so you could cycle through those, make sure you've got them all, make sure you don't double copy any. I believe that is all of them. What about the sets with 3 elements? So A, B, C. And what about ABC? What about ACD? See what I'm getting at? I'm trying to list every combination. ABC, ACD, how about any others that begin with A? ABC, AC, I don't think so. What about B, C, D? Okay. And is that all of the, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, what else is there? Oh, I missed this one. A, B, D. Okay. Now, these are subsets, so technically I can also list that set as well, the entire set. The entire set. These are all subsets. Because remember, I'm not listing proper subsets yet. I'm about to, but since this is just a subset, a list of subsets, I can list the set itself. So let's just note that there are 16. Subsets of a set with how many elements? With 4 elements. Okay, let's just make a note of that for a second. Alright, now what about proper subsets? Now here's the thing though. These are all proper subsets except for that one. Right? These are all the proper subsets. Because subsets are proper subsets except for when they're equal to the, except for the one that's equal to the set itself. So same list, but exclude the set itself. A, B, C, D. So, second note, that there are 15 proper subsets of a set with 4 elements. Alright. Here's the rule. If there are n number of elements, so that's a number of elements, like 5 or 4 or something, in a set, then there are 2 to the n number of subsets, and that same number, but just take that 1 away, because the list is the same for proper subsets, except you've got to take that one set away that's itself. And 2 to the n minus 1 proper subsets. Let me just say something just to make sure this is clear. The empty set is a subset and a proper set of this set. Okay. Earlier I said the empty set cannot be a proper subset of itself, but it is a proper subset of every other set in the world. So the empty set is in both of these. The one that's not is this last one, the whole set itself. Okay, so in the previous example, we had a 4-element set. Right, I had this, so the cardinal number of x is 4, so there are 2 to the 4th equal to 16 subsets. And there are 2 to the 4th minus 1 equals 15 proper subsets. So that's the rule. That's the rule. Cool. So let's look at the next example that asks about number of subsets. I might even decide to change it. Yeah, let's do example 6. Oh, did I not number the last example? So is this example 5 then. We could call the last one 6. It's fine. We'll just call it one of those unofficial examples. One of those unofficial examples in the lecture notes. Example 5. How many proper subsets does the set A equal to the set of all elements such that X is a integer and X is between -3 and 4. How many proper subsets does this set have? Aha, so I'm making you find the cardinal number first. I'm making you find how many elements are in the set before you can find the number of proper subsets. Well, let's list A in roster notation. Okay, gotta remember what integers are. Those are the whole numbers, 0, 1, 2, 3, and the negative whole numbers, so like -1, -2, -3, etc. So, what's the smallest number in this set? The -3. It says x is x is greater than or equal to -3, so -3 is in the set. In fact, that means -2, -1, 0. When am I going to stop? Well, x is less than 4, so 4 is not in the set, but 3 is. There it is. There's the set in roster notation. Now, what is the cardinal number of A? That's the next step. 1, 2, 3, 4, 5, 6, 7. Okay, so the number of proper subsets then is going to be 2 to the 7th minus 1. Exponents first, so 2 to the 7th. Ooh, what is that? 128 minus 1 is 127 proper subsets. Proper subsets. There it is. So this thing has 128 subsets and 127 proper subsets. There are some homework problems in the lecture notes. I suggest you try those. And that's it.